All right, we're live somehow. So before I introduce our first speaker, we're gonna try to figure out how this thing works. So if I can ask someone to raise their hand, just so that we know that this functionality works. Okay, so far so good. Did anyone do that? Benedict, do you see anything?
No, I don't. Should I raise my hand?
I mean, you can raise any hand you'd like.
Hand at the moment, it says.
Raise the hand and then to say that you are ready to enter. So please do that. I try to do it, but since I am in the backstage with you, my camera is taken from here, and then I cannot turn it out in the other one.
Also, I think so. Do I understand correctly that you need to turn on your video, unmute your mic, and then raise your hand?
And do it from my other.
Oh my God! Someone did it. Okay. There's something. Okay, how do I? Oh my God! Yes. Okay. And so now I can admit some people. I'll admit Dan to ask a question. Hi, Dan. Okay, great. Okay, so I think this works. So, folks, in order to ask a question, what you need to do is unmute your mic, turn on your video, and raise your hand, and then we'll admit you and you can ask a question.
Can people hear me?
Yes, we can hear you. Yes.
Oh, yeah. So I was confused. I raised my left hand, and I thought that was what you wanted me to do. But then I looked around, and on the right-hand side, I saw a hand icon. And so I think you were being a little ambiguous.
Yes, certainly we're missing like some typing here. So I see that Raphael also raised hand. So let's see. Oh, wait. How many hands are raised? I'm going to lower all the hands now. Unless, okay. Okay. So I think now we should be good. So I think we should be good to go. And what that means is we're starting HoTT, so welcome to another pandemic edition. And so we're joining you live, I think, from Clouder, which makes you nostalgic for Zoom, which is something I never thought I would say. Yeah, so we have 2 days of great hot talks for you. And our first speaker today is Evan Cavallo, and the topic is cohesive internal parametricity for cubical type theory. One thing that I'll say before I'll let Evan speak is we're very strict on time here. So 50 minutes for our invited speaker. So the stage and the moment are all yours. And you're muted. Oh no. Does Evan need to raise?
Can you hear me now?
Yeah, okay.
Okay, good. Had to get through some dialog boxes. All right. So yes, thank you for having me here at HoTT Pandemic number 2. Thanks to the organizers. Although we are still in the online world, you should know that I did travel across the Atlantic on Thursday, so I at least am providing the conference jet lag experience for you. So I'm going to talk to you today about cohesive internal parametricity for cubical type theory. This is work that I did with Bob Harper during my PhD. He was my PhD advisor. And this is a talk where a lot of adjectives and qualifiers get stuck together to make the title of the talk. So I'm going to go through these sort of one at a time. So to outline the plan here, the first thing that I'm going to start with is this parametricity. So this goes back to John Reynolds, who came up with something. This is probably the part of the talk that's least familiar to the Hot UF audience, so it's also the part I'm going to sort of spend the most amount of time on. And this is some kind of tool which is popular in programming languages, but I have some idea that this could be useful for as a tool for doing higher type theory, like synthetic homotopy theory and stuff like that. And in a way, although it might not be immediately familiar to you, it's connected to a lot of things that you do know about. So it has something to do with univalence that I'd like to get into today. But what I'm going to do is a specific kind of parametricity that's appeared more recently. So initially by Bernardy and Moulin, and then in a subsequent paper with them and also Thierry Coquand. And so this is kind of a synthetic approach to parametricity in sort of the same way that univalence is a synthetic approach to equivalence and variance. And so this is going to sort of strengthen the connection that we have with univalence. And where I come in here is taking this internal parametricity, this internal way of using this parametricity tool, and applying it to higher type theory. So making this cubical version of the system that Bernardy and Moulin and Coquand developed. And then finally, there's this cohesive adjective. So this again is a contribution from my thesis. So Bob was also involved in the development of this, but C. Harper is the paper we have together. C is my thesis. And so this is a addition to the cubical internal parametricity, which was pursued in a similar way by also Nuyts, Vezzosi, and Devriese in another paper working on internal parametricity. And the idea of that is going to be to relate this internal approach to the external version of parametricity. All right, so let's start with Reynolds. So Reynolds, in his paper Types, Abstraction, and Parametric Polymorphism, introduced this concept of parametricity, and I think that he has the best story for introducing it, so I'm going to sort of just repeat that here. So Reynolds' fable from 1983. The idea is you've got these two mathematics classes, so they're maybe complex analysis classes or something. And so on the first day, there's this one professor who's teaching the class, and the square professor decides to define complex numbers using Cartesian coordinates. So he's got the set of complex numbers as a set of pairs, both coming from R, and we have one of these pairs is the imaginary number I, and we have a definition of addition and multiplication on these things. Meanwhile, in the other class, same syllabus, I guess, but with a different professor, the circle professor really prefers polar coordinates. So they define the complex numbers as some polar coordinates, define their I, define their addition, define their multiplication. So that's day one, and each of the students in each of these classes learns that definition. But then there's some kind of mix-up in the registrar, or something weird goes on. You know how it is with administrators. And these professors get switched in their sections. So on the next day, the two professors show up in the opposite classes, and sort of just assuming that the other professor did the same thing, they start developing more operations on complex numbers and proving theorems about them, and so on. And so things could go wrong here, that because they're working with definitions that are different from what they think they are, they end up saying something that turns out to be false. But sort of miraculously, this never happens. So the way Reynolds puts it, neither of them commits moral turpitude. And this is sort of somehow a consequence of the fact that they speak abstractly over this interface. So although concretely the definition of the complex numbers isn't what they're thinking of, they never rely on that fact in what they do in the future. And so they prove theorems that end up being true and do calculations that end up being correct. So in particular, their calculations give corresponding results because they began with two implementations that are somehow related. So although these are two different things, these two definitions of the complex numbers, they have something in common. Or there's some way to connect the one definition to the other. So the question here is, this was a miraculous outcome, but can we formalize some conditions that could guarantee that this would happen? So in what sense can we say, oh, these two definitions are related and they spoke abstractly about them, so they never ran into any problems? And so the goal is that if we satisfy those conditions, then whenever we do some calculations on the complex numbers, our results should be related in the same way that our original definitions were related. Now, you as HoTT participants might be thinking, all right, well, these things are related by an equivalence that preserves the operation. So there's an equivalence between these two definitions of the complex numbers. And so if we speak about them in an equivalence invariant language, such as HoTT or even MLTT, then we shouldn't have any problems. And that may be true, but Reynolds actually has a different answer. So what Reynolds says is, well, I don't need to know that these two things are equivalent. I just need to know that there's some arbitrary relation between them. So maybe I say that A and B are related to R and theta if they satisfy these equations. Now this relation happens to define an equivalence, but we don't really need to know that. We just need to know that it's some relation, and that this relation is preserved by the operations. So the two different imaginary numbers are related. If we start with related inputs and add them in the two different ways, we get related. And if we start with two different inputs and multiply them, we get related results. And we could rephrase these three conditions as saying these three operations are related at different types. So I is related to I at just the type of complex numbers, and plus is related to plus as a binary operation, and times is related to times as a binary operation. So from this initial relation between the two fields, the two complex number sets, we get induced relations on binary operations or ternary operations or so on. Okay. And so that's our notion of related implementation. And then to speak abstractly, Reynolds says, well, talk about these things in simple type theory with type variables more precisely. And so if we start with this interface and write terms in simple type theory, then the results stay related because all of our operations preserve these relations. So if I write I plus I times I, then interpret those things according to the two implementations, that I get things that are related, because at each step, I'm preserving the relation. And same here, if I define a function and interpret it in the two ways, then those results are going to be related at this induced relation on functions. And a sort of nice way to phrase this is that this simple type theory with type variables has a relational interpretation, where I interpret types as relations, and I interpret terms as proofs of relatedness. So here I'm interpreting C as this relation approx C, and then I interpret these terms here as proofs of relatedness between the two different interpretations that I already have. And so looking at a sequent here, if we have an assumption that X is a type and that A is an element of X, and then we write some other element of X using that, then the relational interpretation of this sequence says that whenever I have a relation on two sets, and whenever I have a witness to that relation, so two terms that are related, then applying the set interpretation of M at these two different inputs, A0 and A0, or A1 and A1, will give me related results. Okay, so Reynolds' takeaway here is what's called representation independence. So this is a sort of computer science-y result, which says that we can connect the behavior of different implementations of an interface using these structured relations, so these relations that are respected by the operations. So in this fable, the example is complex numbers, but maybe a more computer science-y example might be that we have an implementation of the abstract binary tree interface as some data type of binary trees versus some data type where we enforce an invariant for preserving balancedness. And the classical computer science application of this is to reason about an efficient implementation using a simpler one. So we might ultimately want to use balanced binary trees because they're more efficient, but if we can relate that to this naive implementation, then we can prove theorems about the naive one and get them to transfer to the more efficient one. So what is univance? This is kind of similar to something that we're familiar with in HoTT, this idea of the structure identity principle as an extension of univalence. So univalence tells us that equivalent types are equal. Structure identity principle tells us when two structures can be considered equal. So and the basic idea is that two structures are equal when we have equivalences between their fields, and those equivalences preserve the operations of the structure. The difference here is that we don't need an equivalence between the types. So for example, with binary trees and balanced binary trees, there are binary trees that aren't balanced. So these two things are not really equivalent. But we can still use Reynolds results where univalence, at least naively, doesn't apply. Now, there is some extent to which you can get by with univalence. So in particular, in dependent type theory, it's often possible to take two implementations that aren't equivalent and make them equivalent by taking some quotients somewhere. So for example, if you implement queues using a list versus using two lists, these aren't equivalent, but if you do some quotienting, then you can get them to be equivalent. And so that I'll plug a paper with Carla and Julie, Anders Mörkberg, and Max Soiner on that, but that's a bit of a tangent from today's topic. There's another application of parametricity that was introduced by Phil Wadler, or observed by Phil Wadler, which is a bit different from the application that Reynolds originally had in mind. So what Wadler observes is that the relational interpretation includes naturality. So here's our sequent with its relational interpretation. It says, okay, this thing has an action on relations, but in particular among the relations are the functional ones. And so if we specialize here to relations that are functions, we get this thing. And if I simplify that a little further, what this says in particular is that whenever I have a function of this type x and some element of the domain, then this function takes the left interpretation, the A0 interpretation of this m, to the A1. So this is a proof that any one of these m's that I can define in this type theory will satisfy a naturality condition. And this lets us skip checking a lot of basic facts. So for example, if you have something that some kind of polymorphic function that acts on lists, you can say, all right, well, this is natural with respect to the type argument to the list type. And Wadler famously called these theorems for free because they follow just by looking at the type. We don't really know anything about M. To get them, we just need to know that it satisfies this type signature, and the naturality in X comes for free. Now, one could imagine trying to play this whole story over using functions instead of relations. But the good thing about using relations is that we don't have to worry about variance. So in this case, the sequent following this X type assumption is sort of covariant in X, or at least if we look at it as a natural transformation from X to X, that's a sort of covariant thing. But when we have like iterated function types and so on, then we get into problems of variance, and this will be familiar to people who have thought about directed type theory at all. So the nice thing about relations is that we don't have to think about that. Okay, so that's actually the application that I have in mind for higher dimensional type theory, this theorems for free one. So in homotopy type theory and related systems, a point of pain is when we try to prove higher dimensional coherence properties. So a kind of infamous example of this is the smash product. So the smash product is an operation, a binary operation of pointed types, which is defined by some higher inductive type. And what we would like to know is, among other things, that this is commutative, associative, satisfies pentagon and hexagon identities that relate iterated applications of the associator in different ways. And all of this stuff should be natural in all the type arguments. But although it's nice to say that we would like to have all these things, it's actually surprisingly, or maybe not surprisingly, I don't know, very unpleasant to try and prove them. So this tower of coherence conditions, and what I've written levels of coherence conditions that you could conceivably try to prove, At each step, you're introducing more identity types, iterated identity types to the mix, and you're also introducing more uses of this match product. So there's an iterated induction on higher inductive types and iterated identity types, and these combine so that you end up having to think about very high dimensional things, and it's pretty difficult to get through these proofs. Bernardy at some point had tried to, and made some progress in trying to write some kind of program to automatically search for solutions to these things because it's so difficult to do by hand. But what Bob and I are suggesting is that we can do away with having to prove all these things by hand using these free theorems that we would get from parametricity. So that's the idea, to take parametricity, which is a classical tool from programming languages, and apply it to the case of higher dimensional type theory, where we have these kind of uniformity or naturality things that we want to prove. And as compared to sort of normal type theory, where we're only usually ever thinking about one-dimensional qualities, these things stack on top of each other and get more and more difficult to prove. So there's some like really difficult things that might be consequences of parametricity, and we'll see that they will be. I just realized that I can't see if any of you raise your hand, so someone please tell me if someone raises their hand. Okay. I'm like in my own world here.
And of course, if you want to ask a question, raise your hand, but also unmute your mic and turn on your video, otherwise I won't be able to see it.
All right. In any case, I'll keep going. Okay, so if that's the plan, then the natural thing to do would be to try generalizing parametricity in the original style of Reynolds to higher dimensional type theory. And there's been plenty of work on parametricity since Reynolds' paper in 1989, generalizing it to more complicated systems. And so we might want to start from Bernardy and Patterson's paper on parametricity in dependent types. But we're actually going to take sort of a left turn here and follow this approach that I mentioned before, more in the spirit of univalent type theory, this concept of internal parametricity. So this was introduced, as I mentioned, by Bernardy and Moulin in 2012 with their computational interpretation of parametricity paper. That was followed by another paper expanding on that idea or doing it in a little different way. And then finally, this paper with Thierry Coquand in 2015, giving what I just copied the title of the first one here by accident, but it's called a pre-sheaf interpretation of parametric type theory. And what I'm going to talk about today is mostly in the style of this last paper, which is sort of the most fully developed, at least to me, version of this idea. And so this is partly justified by, I guess, an aesthetic sense. I like univalence, so I want to do something like that. But there are some reasons to do it, which I'll get to in a second. Let me first sort of fill out this square of different ways of doing things. So parametricity, as I introduced it, as Reynolds did it, is about this metatheoretic interpretation of types as relations and as terms as proofs of relation preservation. So this is all theorems that we prove outside of the type theory. We have this relational interpretation of the type theory. On the other, so that's like an external approach to relational invariance. On the opposite end of this quadrant, we have univalence. In univalent type theory, the action of types on equivalences, the fact that everything preserves equivalences, is a theorem inside the type theory. So that's an internal approach to invariance. But we can also fill in the other two quadrants here. So if we take an external approach to equivalences, what we get is another logical relation, where logical relations are a kind of method of which parametricity is one example. And so what we'd be doing here is giving a metatheoretic interpretation of types as equivalences and terms as equivalence preserving, as proofs of equivalence preservation. And so this is something that has been done. So when we say that even MLTT is equivalence invariant, the way you would see that is by doing this proof, right? In HoTT, we can observe that equivalence invariance internally, but we still have it in MLTT. Otherwise, HoTT wouldn't be consistent. You wouldn't be able to add this axiom. And so the last quadrant here is the internal parametricity. And so that's where the action of types on relations, relational invariance, is a theorem inside the type theory. So we're going to take this fact that was previously external and we're going to pull it inside. So as I started saying before I remembered the order of the slides, there are some reasons to do this besides just liking it. So one thing is that we're going to use parametricity in pretty complex ways. So I won't be able to really spell that out in this talk today, but we're going to be proving iterated coherences of this smash product, for example. And those proofs will be nicer, at least I believe, than trying to do these things by hand, but they're still pretty involved. And so if we have to step outside the system to prove them, it's a little unsatisfying. In particular, if you're someone who likes formalization, which I do, then you're stepping outside of this framework where everything is verified to get these metatheoretic results. And that's a little unsatisfying. So if we could bring that inside, then it could be part of our verified system. In addition, there are sort of applications in the other direction. So I've primarily been talking about internal parametricity as a tool for higher dimensional type theory, but the system of internal parametricity also gets better behaved if we build it on top of univalent type theory. So I think many of us will agree that HoTT is HoTT, or if you insist on computation, cubical type theory, has a lot of good properties that are lacking in, say, intentional type theory, things like function extensionality, or the fact that we understand what qualities in the universe are. And so that same kind of situation will apply here. We'll be able to characterize the identity types of internal parametricity primitives and so on in ways that we wouldn't be able to in this internal parametricity theory that was developed by Bernardy and Moulin. And then there's finally a kind of expository motivation towards these things. So internal parametricity, as I've been harping on, has a relation with HoTT. There's a similar setup. And in particular, the way internal parametricity is realized by Bernardy and Moulin has a lot in common with cubical type theories. That's not something that they weren't aware of. My understanding is that the development of the Coquand-Huber original cubical model of HoTT was developed physically very closely to internal parametricity, like by people in the same place talking to each other. So they knew that these things were related to each other, but I hope to spell that out a bit more and you can see it for yourself. And for me, part of this wanting to do this is to learn more about the mechanics of higher dimensional equality from internal parametricity. So we kind of have these two systems that have a lot in common, and if we want to understand the broader world of internalizing these kind of invariance principles, then it's useful to have multiple examples. We have HoTT, and here's something else that you can think about, and maybe it will help you to think about it. So the key property is the equivalent of univalence for internal parametric type theory. And so where in univalence we have a correspondence between equivalences and identity types or paths, here we're going to have an equivalence between relations, and here these relations are going to be type valued. So rather than being some kind of subtype of the product of A and B, it's going to be a type valued predicate on A and B. And these are going to correspond to something called bridges. So the name bridge comes from the Nuyts, Vezzosi, and Devriese paper for relational-like things. So the type-valued relations will correspond to these bridges in the universe. And then we're going to arrange so that sort of by definition, every construction has an action on bridges. And then from this equivalence, we inherit that everything has an action on relations. So again, the comparison with univalence looks like that. And by sort of definition of identity types in general, not specified to the universe, all constructions preserve identities. And so if we know that equivalences are the same as some kind of identity, then all constructions will preserve equivalences. All right. So now I'm going to introduce to you a roughly the same type theory that is introduced in this Bernardy Coquand Moulin type theory paper. And so the game plan, it takes always a little while to introduce a full type theory. So I want to make clear here when you'll know that the definition is over. First, I'm going to introduce interval terms. So this is sort of the basic judgmental structure of internal parametric type theory, which is a characteristic shared with cubical type theory. Then we're going to introduce those bridge types, which are going to essentially internalize interval terms. Then I'm going to talk a little bit about function types. So we always seem to end up talking about function types. We talk about function extensionality a lot in HoTT. This is sort of the analogous section to that. And then finally, we're going to talk about the analog to univalence, which is the relativity principle. And for that, we're going to introduce one last thing, these gel types. So this is just essentially the BCM theory, but I'm going to present it in my own notation, which is a little bit more similar to the cubical type theory notation. So maybe clearer for you, it's at least clearer for me. And so we'll see those parallels with cubical type theories. I want to do this without introducing all of cubical type theory first, so sorry if that's not super familiar for you. But just to recall the basic thing, we give a computational interpretation of, or we can give a computational interpretation of HoTT by replacing these identity types, or interpreting these identity types of HoTT as path types. And so a path will be a term that varies in a variable from a special interval object. So if I have a term m that varies in x in the interval, that's going to be a path, and that path connects the 0 endpoint, where I plug in 0 for this interval variable, to the 1 endpoint. And so I form an element of this path type by abstraction. Okay, so starting with the interval terms. We begin with Martin-Löf type theory, and now we add a new judgment for these interval terms. So in any context, I can talk about what the interval terms are in that context, and I have two constants, one called 0 and one called 1. And so we think of this interval as being a line that's connecting 0 and 1. We don't have any explicit constant references for the stuff that's in the middle, but it's not excluded. This is sort of an abstract interval. And so we have those constants 0 and 1, and of course, if we have an interval variable in the context, then we can talk about those variables. Those are terms too. And so the idea here will be that if I have a term varying in an interval, then as that x varies from 0 to 1, it's going to draw out a line in this type A, which we call a bridge, and that bridge is connecting whatever we have when we plug in 0 and whatever we have when we plug in 1. Now, for internal parametric type theory, it's important, maybe more than in cubical type theory, that we notice that this type A can also vary in X. So more precisely, when I have a sequent like this, I have a type that's varying in I, and then in the sort of total space of that line of types, I have a line from M0, which lies in A0, to M1, which lies in A1. And this line of M's inhabits that line of A's. Now, in HoTT, we also have the notion of a heterogeneous identity type, maybe defined by transport. In cubical type theory, it's a primitive thing. In those cases, we can kind of reduce the heterogeneous version to the homogeneous version by adjusting by a transport. But because we won't have transport here, it'll be more important to think of the heterogeneous version by default. And the intention, again, is that when we have a bridge of types, that's going to correspond to a relation on the two endpoints. And then if we have a term inhabiting one of those lines, so both M and A, again here, can depend on X, that stands for a witness to that relation. So if I have M in A, that's saying that the 0 endpoint of M is related to the 1 endpoint of M according to the relation that's represented by this type A. And so if I go back to that sequent that we had before, where we have a type hypothesis and a term hypothesis, and then we construct another term in the same type, and here I'm making the dependence on these two variables explicit. If I then introduce a interval variable to that sequence on the left here, then that means that I want to read this sequence as saying, so now each of these entries after the x is taking place in a context with an interval variable, so I read them as being relations and witnesses of relations. So this sequent will kind of represent the fact that for any relation I plug in for A, so some R relating A0 to A1, and any witness to two terms A0 and A1 being related, I'll find out that the output applied to either the things on the top or the things at the bottom is going to give me related results. And so the application of the parametricity theorem in an internally parametric type theory takes place by weakening. So when I take this sequent, which is just saying, given a term in the universe and a term of A, I spit out a new term. When I weaken that into a context with a dimension variable or an interval variable, now I'm able to plug in relations and witnesses to relations for these hypotheses and get out a witness to relatedness from the consequent. Okay. Now, one thing that's a bit odd about the interval terms of parametric type theory compared to, say, cubical type theory is that we need these variables to be substructural, and specifically affine. So what does that mean? Well, our ordinary variables in type theory obey what are called structural rules. So there are 3 of these. They are called weakening, exchange, and contraction. So weakening says that if I have a variable, I can always not use it, so I throw it away. Exchange says that I can switch variables in a context. So if I've assumed 2 interval variables, then I can use them in the opposite order. And contraction says that if I have 2 interval variables, then I can plug in some other interval variable for both of them. So I have 2 separate things, and then I identify them. And it's this third contraction principle that affine variables do not have. So substructural in general means that one or more of these principles is missing. Affine means specifically that contraction is missing. So we're going to be forbidden from taking 2 separate interval variables and substituting the same thing for both of them. So this appears a lot all over the place in type theory. So it's often used when variables represent resources. So you don't want to let someone use the same resource twice. So you forbid this contraction. If you want to make sure that all resources are used, you get rid of weakening and so on. One particular place it shows up is in nominal sets. So this uses an intuition of affine variables as names. And it's used, for example, to talk about logics with variables inside of a type theory. So from, it's kind of a, if you want to reason with variables inside of type theory, that's kind of hard to do because you have to think about these things like substitution all the time. And so if you try and build those properties in, you get something that looks like affine variables. But the closest application to the one that we're doing today is the BCH cubical sets model of HoTT, is on Coquand and Huber. And this is the first cubical sets model of HoTT, the first computational interpretation of HoTT. And they use also affine interval variables. So in our paper, which, and in this we follow Cheney's dependent nominal type theory, we have a substitution calculus for affine variables, which uses a restriction operator on context to express these things. So we have weakening for these variables. And then if we want to substitute something for a affine variable, then we can pick some variable to substitute for it, some R. It should be an assumption that R is in delta here. And then for the rest of the substitution, we're not allowed to use R anymore. So this \R is removing R and the term hypothesis that come after it from the context here. And so that prevents us from doing these kind of diagonal substitutions where we use the same thing twice. So we can substitute R here, but then when we're writing down the rest of the substitution, we're not allowed to use R again. So these imply the other structural rule exchange of interval variables, and also apply that we can exchange interval variables with term variables in one direction, but not the other direction. So you can think then of adding an interval variable to the context, if this is helpful, as some kind of not Cartesian product with the interval, but some kind of monoidal product with the interval. So term hypotheses are Cartesian product, but these other ones are not. And so then you get these differences between assuming things in one way or the other. There was something that I wanted to say here. No, there wasn't. Okay. So once we have that judgmental structure of the interval variables, we can start internalizing that with the bridge types. So these, we'll say whenever I have a line of types and I have two things lying in the endpoints of that type, I can form the type of bridges. And a bridge between two things will be just a term over one of these variables. So this is going to be a witness that M0 and M1 are related over the relation represented by A. And these behave like function types, albeit affine function types. So if I want to form an element of the bridge, I take something, a term over a variable, and abstract that variable. Write lambda for it if we like. And likewise, if I have one of these bridges, then I can apply it at some interval term. And the affine discipline requires that the interval term I apply with is separate from the function. And these types of the relativity equivalence, saying that if we have a bridge in the universe, then we get a relation out of it. And that relation will say, all right, two elements A and B are related if there is a bridge over this bridge in the universe between those two things. So this matches the intuition I've been pushing on you all along. And so that will give us one direction of this equivalence. And for the other one, I'm going to introduce a new type former. But before I get to that, I want to talk a little bit about function types. So what is a bridge in a function type? Well, according to our intuitive picture, which I've changed a little bit, but mostly the same, if I have a sequent in a context with a dimension variable, interval variable, then I should read what comes after as being some function of relations and witnesses to relations. So here, for all relations and for all witnesses, I get two witnesses between these two outputs. And so a function becomes a function taking related inputs to related results, or witnesses for those things to witnesses for those things. And so if we have a bridge, so now I've just taken that sequence and internalized it, first by forming a function type and then by forming a bridge. It's not the same sequence here, it's just a arbitrary A to B. So if I have a bridge between two functions, then I can indeed get a function from bridges in the domain to bridges in the codomain out of that. So if I have any 2 points in the endpoints of the domain type A, and I have a bridge connecting them, then I can apply pointwise this bridge of functions to this bridge of inputs to get a bridge of outputs. So for every x in the interval, I apply q at x to p at x, and that will give me a bridge between f0 applied to a0 and f1 applied to a1. So that's fine. Then there's the question of the other direction. So if I have a function from bridges to bridges, do I get a bridge of functions out of that? And that's something that's also important to have. So here's what I'd be starting with here, this h, which given any two related things produces related results. To construct this bridge in the function type, it turns out that we need a new primitive operator. So this is our third thing. First we had interval terms and bridge types. Now we have an operator which I call extent. And so let me just show you what the element of this bridge of function types would look like. So I'm constructing a bridge, so I take in an element of the interval, and then inside that I'm constructing a function, so I take in A. And then I want to say that somehow this A, which depends on, or is somehow in a context with X, represents some bridge. So as X varies, A is varying somehow to form a bridge in the domain type. So extent is kind of a case analysis, which says, well, what's X? If X is 0, then I just have this point A0, which lives in A at 0. And in that case, I want to apply this function from the left. So I have two functions on either end. I'm going to apply the f0 to my a0. If instead x turns out to be 1, then I've got a is some point a1 living in a1, and then I apply the function on the right. But if x is a variable, which it sort of happens to be in this case, then I can say that A is the instance at some variable y of a bridge that goes over A, connecting 2 points A0 and A1. And if that's the case, then I'm going to apply this input H. I'm going to say, now I have a whole bridge, so I'm going to apply it to my H that gives me a bridge in the output. So somehow extent lets us realize that any interval term has got to be either an endpoint or it's a variable. And so if we have a term A in that context, then either it's going to be an inhabitant of the left endpoint, an inhabitant of the right endpoint, or the sort of center point of a bridge that's going all the way across. So the general form of this thing, and I'm sticking to non-dependent function types A, arrow B here for simplicity, but anyway, the general form of this thing is going to take in an interval term and some arbitrary term M, and then tell me whether I'm in one of these constant cases or in the variable case. And the kind of typing rule for that looks like this, although this R should be a 1. I think maybe it's not worthwhile to spend a lot of time on that. But operationally, what that's doing is, in the case where R is a variable, M is allowed to mention X, and we're going to pass into that variable case by supplying M with X abstracted. So we're taking that variable X that can occur in M and sort of capturing it, and we have this whole bridge. And that's where the substructurality is so important. So the process of taking a variable in some term and capturing it, abstracting it, is something that doesn't behave well with contraction. So I think I'm low enough on time that I shouldn't spend much time going through this diagram. But if I identify two variables, then the things that I'm going to capture when I abstract are going to change. So some variables can get captured in. This is sort of a classic mistake that people make when they're beginners trying to implement programming languages, is that they get this capture avoiding substitution wrong. But if we have substructural variables, then this problem doesn't arise, or affine variables in particular. On the other hand, if we work with structural variables, we get a different principle from the one that we want, identifying bridges of functions with bridge-preserving functions. And that's the function extensionality principle, which is familiar from HoTT and Cubical type theory, where a bridge of functions is a point-wise function of bridges. So that's a little different. Now, the final component of internal parametric type theory is the inverse to that candidate relativity map. So what we have so far is something that takes a bridge in the universe and gives us a relation on the endpoint types. And so there's going to be one last type former that's doing exactly this. So taking a relation and producing a bridge of types from it. So it's going to be a type former that takes a relation and takes a bridge term. And it's going to give us sort of a line in that bridge term, which when it's 0 becomes A, and when it's 1 becomes B. And the inhabitants of that gel type are going to be witnesses to the relation. So whenever we have a witness to the relation, we get an element of that gel type which lies over it. And again, connects the left thing to the right thing. And there's some elimination form for this and some beta and eta laws for it, but I won't get into that. So briefly, the way that this all works, if we have some function like this, and we have a relation and a witness to that relation, then we can turn that relation and witness to the relation into bridges using the gel types, apply the function to those things in a context with a bridge variable, and then abstract the relation out. So this is the picture of how a function gets applied to relations, because we know that everything can be applied to bridges, which are just terms in some extended context. And then from that, we get that we have relations to relations. The extent doesn't come into play here. That comes into play when we have types that involve sort of iterated function types to the left. So for example, in this type. Okay, so that's the BCM case, the simple internal parametricity case. What Bob and I do is replay that story on top of a cubical type theory. So the aim, again, is to apply parametricity to these higher dimensional coherences. And so what we need to do for that is show that the internal parametricity primitives support the structures necessary to exist in a cubical type theory, and those are coercion and composition. And so our type theory is grounded in a computational interpretation. We prove canonicity for it. And like in cubical type theory, what becomes the key thing that we have to settle is we have to consider evaluation not only of closed terms, but closed terms in context with interval variables. And in particular, the elimination form for the gel types evaluates terms under an interval binder. We also give a pre-sheaf interpretation of this extended theory following the BCM pre-sheaf interpretation. And so cubical type theory is also introducing these interval terms for paths. So here, again, a term in an interval context represents a path in the type. And something that doesn't appear in internal parametricity, types and terms of cubical type theory need to support coercion and composition of open boxes. So we can coerce terms. If we have terms living in one endpoint of a line of types, we can get something in the other endpoint. And if we have an open box, we can compose it. So that gives us transitivity and symmetry and things like that. So these are all there to ensure that paths in the universe induce equivalences. So we use these things to prove that. And so these things don't appear in parametric type theory because we only need to know that paths induce relations. So our theory combines those two things, and we have interval hypotheses for both directions, two different kinds of interval. And we really only need to make one change to the basic cubical type theory setup, which is to allow the boxes that we compose to have a kind of horizontal extent in bridge directions. So we can compose boxes of paths like before, but we can also compose something where this horizontal P is not a path, but a bridge. And so this means that we can, say, adjust the endpoints of a bridge by some paths, basically saying that the indices of a bridge type respect equality, which they certainly should. But we can't compose in the direction, the downward direction of a bridge, because we don't have essentially coercion, because relations are not always equivalences. And so that's necessary to compute the coercion composition in bridge types. But again, we only have coercion in the path direction. So other than that, there's just a bunch of technical stuff implementing this coercion composition, but that's really the basic idea of it all. And then it's useful for, I don't know, enlightenment to think about how these things relate to each other, cubical type theory to internal parametricity. So we use, as our cubical type theory, Cartesian cubical type theory. So this is the one developed by Julie Fafoni and Harper. There are, of course, other variants of cubical type theory, like the De Morgan one, as well as the BCH cubical model. So the BCH cubical model is the one most similar to internal parametricity that does use. But for cubical type theory, it's kind of not so great as the structural ones. So for one thing, affine variables are just less familiar, so it makes it a little more annoying. But they also have big problems with modeling hits, so that's kind of gone out of fashion. And we don't need those two things to be the same, the path variable and the bridge variable. In fact, really, there's no need to have much of a relation between them at all. Now, for cubical type theory, this problem of the characterization of functions disappears. If you have coercion, then those two characterizations, the one where you have a pointwise family of bridges and the one where you have a proof of bridge preservation, are equivalent. So you can look here and find a contractible singleton that makes these two things the same. But we don't have coercion, so we're stuck with the substructural version. That's kind of why both versions work for cubical type theory, but only the substructural version works for internal parametricity. And I really don't have time to talk about this, but there are two different approaches to univalence that you would use depending on whether you've got substructural or structural variables. And so that's, I think, a very interesting thing to work out, but I won't do it today. And we get some bonuses, as I mentioned before, as a result in our theory of working with equality. So, for example, we can show that a path between bridges is the same as a bridge between paths. So that's kind of the equivalent of function extensionality for bridges. And we use both function extensionality and univalence to prove this relativity principle. And in the original BCM theory, these are instead postulated as exact equalities. And so this is, it's sound, and it doesn't, I believe, still fine as far as computational interpretation is concerned, but it's a little harder to model. So they have to make some changes to the sort of basic pre-sheaf setup to get this thing to hold, which we don't have to worry about. And you can see why those things are needed here, because to prove the inverse conditions here, you're going to be proving equalities in a function type involving the universe. And finally, we can go ahead and prove those coherence results that we were hoping to prove. So in our paper, we show, for example, that if you have some polymorphic function doing something with a bunch of smash products, then you can characterize it as being one of two things. And we can use that to show that any commutator or associator satisfying very simple conditions that are easy to check are equivalences, satisfy the Pentagon identity, and so on. And we prove this sort of uniformly as things get more complicated. So there's an induction on n going on here, but we're only doing induction on one of these smash products at a time. So there's not like a real stacking of complexity as you go on. Okay. So that's the paper with Bob. And now finally I want to talk about this cohesion thing that I teased you about in the beginning. So
let's be brief though. Let's be brief.
Yes, we will be brief. So if you've been paying attention, you may be thinking that I'm slipping something under the rug, and I am. We show that internal parametricity is useful for proving these theorems, but then those theorems only apply to internally parametric models, which doesn't include the standard models of interest. So in the original Reynolds picture of parametricity, you can interpret type theory and set theory, and then you know that when you start with some term, it gets interpreted as a parametric family of elements in set theory. But of course, not all families in set theory are parametric. In the Bernardy Moulin picture, you have this parametric type theory, but you can't interpret it in set theory anymore because you can prove inside it that all terms are parametric, and that's not true in the set theoretic model. So instead, you have to do this pre-sheaf model in cubes, and that's all well and good. But if you had your original model where you wanted to prove theorems of interest, then you're stuck. So you could have some thoughts about what to do that I'll skip because there's no time for them. But maybe a way to solve this would be to create a system that has both a parametric mode and a non-parametric mode. The non-parametric one of which could be interpreted in your original theory of interest, but where you can somehow get theorems from the parametric mode to help you out. So this was done in some way by Nuyts, Vezzosi, and Devriese, who gave also an internal parametric type theory. So they do something of this kind, and it's used for a couple of different purposes in there. So I really would love to spend more time on this paper because it's very relevant to internal parametricity. And they do things that are different from the way I've presented things, like using a structural interval. And in order to get that stuff working, they need a system like this. But the way all that works is it's axiomatic cohesion, which was introduced to type theory. So it's introduced by Levier for categories, and then Schreiber and Schulman brought this into type theory. And so I, in my thesis, applied this to internal parametric type theory. And the idea is that you have two modes of judgment interacting in a single type theory, a parametric mode and a pointwise mode. And there are a bunch of contexts and type formers, something like 4 of them, that relate these things. And so the parametric mode gets interpreted as pre-sheaves and the other one as regular stuff. And so the type formers look something like that. Gotta hurry.
I'll just say that the next thing on the agenda is a break. So in 2 minutes, we will have a choice of going to break or staying in the discussion room. So I'm just going to say, stay in the discussion room.
Okay.
Evan can continue.
I'm almost done.
I've been hearing that a lot.
All right, so, right, where was I? These are sort of things I've already said. So concretely how this works is if I have some term in the parametric mode, I can use these things that convert between the two modes, which I will not give in detail, to turn that into something in the pointwise mode. So every kind of parametric thing is a regular term plus a bunch of facts that it preserves stuff, preserves relations. And so I can just take out the sort of 0 level piece of it and get something in the pointwise mode. But because I know it came originally from the parametric mode, I get to see that it satisfies parametricity theorems. So this is going back to a sort of Reynolds style approach to things, where terms that I can define inside this restricted world, which for Reynolds was simple type theory, but for us is this parametric mode, satisfy universal uniformity theorems even when I interpret them just as point